Now that we have been introduced to the concept of reactance, we are ready to find mathematical expressions to calculate the actual values. So let's go. I have this set of diagrams with the equations, and we are going through to derive expressions for the reactance, capacitive reactance and the inductive reactance. Before we go through the reactance, let's refresh our minds with Ohm's law that applies to pure resistance. So with Ohm's law, we have the voltage across a resistor being equal to the current through it multiplied by the resistance of the resistor itself. It can be vice versa. We can write it as R. Multiplication is commutative, so instead of IR, we can as well write it as RI. So what we have here is the resistance of the resistor itself. Now, if the source of power is sinusoidal or is alternating current, then we expect that the value of the potential difference across the resistor will depend on the value of the current. So if the current is high, then the potential difference will be high. If the current is zero, the potential difference is zero. So if the current is in the opposite direction, the potential difference will also be in the opposite direction. So if we plot a graph of the whole thing, we realize that the current is in phase with the potential difference across the resistor. I've explained to you what in phase means. In simple terms, whenever the current reaches its maximum, the voltage or the potential difference also reaches its maximum. When it is zero, it also drops to zero. When it is in the negative direction, it also goes like that. So just look at the curve and it tells you what we mean by current being in phase with the voltage. This is for the case of pure resistance. Let's move on to capacitance. We have a capacitor connected to a simple circuit here. We should recall that the capacitance has this definition. The total charges on it, on a capacitor, will be equal to the capacitance multiplied by the potential difference across the capacitor. So capacitance is defined as the ratio of the charges stored on the capacitor to the potential difference across the capacitor. So from this expression, we come out with this. Alright. If we differentiate the amount of charge being accumulated on the capacitor with time, then we get a current. That's dQ dt gives you the current. And from the handout, we've stated that let the current be given as a sinusoidal. So we have the current being equal to a maximum value, which is I naught cos omega t. So in the handout, we are going to use this value or this expression for the current. It's sinusoidal. We are using the cos part or the cos aspect of it. It's the same thing. It's quite easier to handle it this way. So the current, the sinusoidal current, is given by the amplitude, the maximum current that can flow, cos omega t, omega being the angular frequency. Sometimes compared to other sinusoidal, it might have a phase difference. That means it may not start exactly from zero. There may be a phase difference. If the phase difference is not zero, we don't want to go so much into that. Let's move on. So the current, we are taking the current from the handout. The current is equal to the maximum value cos omega t. That means if we differentiate the amount of charges accumulating on the capacitor plate with time, we get a current, and the current has been given as this. From this level, we can decide to integrate through. If we want to integrate, that's we are taking this current out. We are starting from here. You can see. I don't want to waste time, so see what I mean. Yeah. Okay, so we just multiply through by dt, so that the t comes here, and we leave the dq here, and then integrate both parts of the equation. This one is a constant, so it can come out of the integral. Then if we differentiate 1 with respect to q, we get q. That's the quantity of charge. And when we come here, if we differentiate cos, which is also a function of another function, then we are going to get sine. But then we have to divide everything by the coefficient of the function inside. This one will be like polynomial. If you differentiate omega t with respect to t, then you get omega, the constant attached to it. That one will be divided by what you get by differentiating omega t will be a denominator that is placed here. You can go through your integration again to appreciate what we are doing here. We are done integrating this function here. So the quantity of charge is given as the maximum current flowing divided by the angular frequency sine omega t. Now, verify for yourself from Trig Identity that sine omega t can also be expressed as cos omega t minus 90 degrees. We can replace the quantity of charge being equal to capacitance multiplied by the potential difference across the capacitor. So Q is equal to this. So instead of Q, we are putting this expression. So here we are, instead of Q, we put the capacitance multiplied by the potential difference across the capacitor. That still becomes I naught over omega t cos omega t minus 90. Alright. We can now divide through by capacitance so that we have this expression here. This is quite simple. From here, just divide through by c, and the c will become part of the omega at the denominator there. Now, we can have a general expression for the potential difference across the capacitor. That will be equal to the maximum potential difference. You see, the potential difference is also varying by itself. So the maximum potential difference we can have, that will be the amplitude, cos omega t minus 90. Therefore, we can say this maximum value of the potential difference across the capacitor is equal to the value here. So that's what we've written here. V naught is equal to 1 over Wc times I naught. Comparing this one to the Ohm's law, comparing this with the Ohm's law, we have here I and we have here R. This is the potential difference across the resistor. So we have here the potential difference across the resistor being equal to a certain value here multiplied by the current. So this one is analogous. It's analogous to the resistance. But I've told you it is quite different from resistance because it does not dissipate energy. So this is the value that we call the reactance. Reactance. So because it's the capacitor, we are calling it capacitive reactance, which is equal to 1 over omega c. So if you are given a capacitor with its capacitance, and there is an AC flowing through the capacitance, and you know the angular frequency of the AC, then you can tell the reactance of the capacitor. You can tell the reactance of the capacitor by finding the inverse of the product of the angular frequency and the capacitance. So this is what we call the reactance, the capacitive reactance of the capacitor, analogous to the resistance of the capacitor, but we don't call it resistance. I've explained that one again and again. We call it the reactance instead. Okay, we can go through the same similar procedure with the inductance. Let's see how it goes. Let me make it a bit bigger. Okay, so here we are. We have an inductor that is connected to a resistor and then an alternating source. At any instant, there is a current flowing through it with which is denoted by the letter I. This letter I still has this letter I still has its cause issue. So there we are. But from Faraday's law and from inductance, from our lesson in inductance, we came across this expression. Let me quickly remind you of that expression again. Here we are. So we came across this one. So the potential difference across the inductor at any moment is given by the negative of the inductance multiplied by the time rate of change of the current. So that gives us the inductance. That's what we are we've written here. So if the current is I, then we can put this one here there instead of the I. So you put it here, I naught cos omega t instead of the I. Then we differentiate. We find the differential. After finding the differential, there's a negative here. I think we may not be so much concerned about that. So if you differentiate this one, it's a function of a function. Cos is a function, and cos has another function within it. That's omega t. So after differentiating cos to get sine, you need to differentiate what is inside cos to get omega. So after differentiating cos, you get negative sine. This is how come the negative comes in. All right. Then there's a trig identity, a trigonometric identity that we need to remember. That sine omega t can be written as negative cos of omega t plus 90 degrees. Verify this one for yourself. All these are in the handout, so I need not write the whole thing again. You can verify all the whole thing for yourself. So we can now conclude that the voltage across the inductor can be given by the angular frequency multiplied by the inductance multiplied by the maximum current. All these together form the maximum potential difference across the distance. So we can write V naught being equal to omega L I naught, so that this one will represent the reactance, inductive reactance. Alright, so there we are. So this is the inductive reactance. This is what we've been chasing for all this while. So this one is also analogous to the Ohm's law. So that if we have the voltage across it and there is current flowing through it, then the coefficient of the current becomes the resistance. This time, I tell you again, we are not calling it resistance, we are calling it reactance. Resistance and reactance react to the current that flows through them, but the difference is that resistance dissipates energy, but the reactance do not. We have capacitive reactance, we have inductive reactance. This one is inductive reactance. So if you know the inductance of the inductor, and you know the angular frequency of the current flowing through the inductor, then you can talk about the inductance. How is it resisting the current flowing through it? You can talk about the reactance. How is it resisting the current through it? So this is reactance. Alright. There's one more thing we need to talk about. The phase difference. We talked about the phase difference for the pure resistive AC circuit. Now let's talk about the pure capacitive circuit. So here we are. The current is a cosine. The current through the circuit is a cosine. And cosine curves start from maximum at t equals 0. They start from the maximum and start descending. So by a quarter of the cycle, they are at 0. Then after another quarter, they will be at their minimum, the minimum value. Another quarter, they come to 0. Then the last quarter, they are at their maximum again. This is a cosine. That's what we have the I. The I is I naught equals, I is equal to I naught cos omega t. So this will be the curve. When t is 0, we have I naught cos 0, which will give us I naught here. So this will be the value. Okay, so that's it. Now that's it. So we were replacing this one by CVC. So in other words, this VC, which is varying, the capacitance does not vary. The capacitance of a capacitor is a constant, so it doesn't vary. So this one is varying as the sine. So more or less, this one is a sine function. We are only trying to write it in terms of cosine so that we can understand the relationship. So here we are. The VC is a sine curve. It starts from 0. By a quarter of the cycle, it reaches its maximum. By the next quarter, it comes back to 0. The third quarter is at its minimum. Then by the last quarter, it will be back to 0. So that's for the sine curve. Now, what's the relationship between the sine curve and the cosine curve? You will notice that at time 0, the cosine curve will be at its maximum. Then, after a quarter, the cosine curve, the sine curve will now reach its maximum. When the sine curve is at its maximum, the cosine curve will be at 0. Then the sine curve will now be following it. So we can see that the cosine curve is leading and the sine curve is following. When the cosine reaches its point, a certain point, the sine curve will reach that same point after a quarter of a cycle. So by 90 degrees or a quarter of the complete cycle, when the cosine has already reached its peak, the sine curve will now go to its peak, and in that order. So we say the voltage across the capacitor, so it's lagging behind by 90 degrees. Then if we should go by the same understanding, if we should plot the cosine curve for the current, it will be the same thing as the current through the capacitor. So it will move this way. Then we can also have the negative sign. The negative sine curve. If we have negative sign, it's simply the sine curve, but it is negated. So instead of positive value, it will be negative value. So it's the same sine curve moving up and coming down, but then the maximum value will be negative. And then the negative value, which would have been here, will now be positive. That's all. So this is the sine curve. The same thing, but it has been negated. Now, let's look at that one also. So you realize that when the sine curve is at 0, the cosine curve is now trying to arrive at 0 within a quarter cycle, the quarter of a cycle. So this time around, the current is rather following the voltage across the inductor. So the current is following the voltage across the inductor. So the current rather lags, or the voltage rather leads. Is the same thing. Let me write it somewhere. The voltage across the, the voltage across the inductor leads by 90 degrees. In other words, the current lags the voltage by 90 degrees. Alright. So go through the whole video again and convince yourself what I'm trying to explain here. The final thing I would like to state is that the voltage across the capacitor and the voltage across the inductor are out of phase. So when the voltage across the capacitor is at its positive peak, the voltage across the inductor will be at its negative peak. You see, so they are more or less opposing each other. So the voltage across the capacitor will be at its maximum peak, while the voltage across the inductor will be at its minimum peak. If you should cut the whole thing and place it here, then you will get something like this. So these two curves are out of phase, 180 degrees out of phase. Yeah, so read about that one also. Alright, so that's it for the reactance. The next lesson, we'll put the two reactants together. We assume the capacitor, the resistor, and the inductor are in a circuit. So we put all their action against the current together, and we call it impedance. That will be our next lesson.